In math, limits come in all different shapes and sizes, which unfortunately can make things a little difficult for us poor math students, because we're not able to just throw these into an equation and call it a day like the quadratic formula. No, instead we need to use a diverse set of methods and intuition to solve these. Doesn't that just sound fun? So let's go ahead and learn some of the most common methods in order to derive these. Alright, so here we have our first fundamental method of solving limits, the difference of squares formula, our bread and butter pretty much. And it simply states that a squared minus b squared is equal to a plus b times a minus b. Not too bad, and you've probably already covered this actually in studying polynomials. And yes, I know, this is actually useful for something. It's a miracle. So, coincidentally, this just so happens to use the difference of squares that we can recognize here. We have x squared minus 9, which means that we can actually apply this difference of squares formula to reframe it as x plus 3 times x minus 3 over x minus 3. And since we have common terms here, we're multiplying by x minus 3 and we're dividing by x minus 3, well, we can just cancel those out, and that gives us x plus 3, which when we use direct substitution, we'll just get a 6. And now we're not evaluating to that pesky indeterminate form, because if we had tried to just preemptively plug 3 in, well, we would have just gotten 9 minus 9 over 3 minus 3, which I'm sure you don't need me to tell you is indeterminate form. That gets us nowhere. And now that we've gone ahead and factored this, we know that the answer is actually 6. So we can say this evaluates to 6. Voila, there we go. Beautiful. Now, another helpful thing we can do is we can take this difference of square laws and apply it to values that aren't strictly speaking squares. So we have this x here, which quite obviously is not a square, but what we can do is we can use some simple intuition to convert it into one. So we have x, and we can go ahead and rewrite this as being equal to the square root of x squared. And now we can go ahead and recognize that we can use the difference of squares here. So we can convert this x minus 4 into the square root of x minus 2 times the square root of x plus 2. And voila, there we go. And all we've done is just convert this into the square root form, and we've taken this, converted it into 2. And then we're applying this difference of squares law. No problem. And then we can go ahead and add this up here so we can factor it. So we have square root of x minus 2. These will cancel out, quite obviously, and we're going to be left with a 1 in the numerator. So that gives us 1 is equal to square root of x plus 2. And now that we've solved all that, we can go ahead and use direct substitution. So that gets us 1 over the square root of 4 plus 2, or 1 over 4, which means that this entire limit will evaluate to 1 over 4. Another example of our bread and butter. Speaking of polynomials, I hope you didn't expect to get better. No, my friend. In calculus, things only get worse. So here we have our next limit to solve. We have x squared plus 5x plus 4 over x plus 1 as x approaches negative 1. And here, what we're able to use is a different technique. We can go ahead and simplify this polynomial to see if we can't go ahead and factor out this x plus 1. Now, I don't think it's too outrageous to assume if you're watching this, you know how to solve a polynomial, so I won't go over it in too much detail. But just as a brief recap, what we're able to do is we're able to take a polynomial like this, and we're able to divide it up into a and b to solve for the roots. So that's what we're going to do here. So we can figure out what a and b is pretty easily. So we have a plus b is equal to 5, and we have a times b is equal to 4. Now, just looking at this, I can tell you pretty easily that this is going to be 4 and 1. We have 4 plus 1 is 5, 4 times 1 is 4. Awesome, which means that we can go ahead and simplify this polynomial as being equal to x plus 4 times x plus 1. And then, when we go ahead and factor in this x plus 1 from our limit here, well, we have something beautiful that happens once again. We're able to go ahead and factor out the x plus 1. That leaves us with x plus 4. And then we can use direct substitution, and voila, we have 3. That's pretty simple, right? So we can just say this evaluates to 3 and move on. And just as promised, things are getting worse, and now we have the famed quadratic formula involved. I hope you remember it. So for more complex polynomials that we might not be able to solve at first glance, we're able to go ahead and apply the quadratic formula in order to find the roots. And as long as you remember the quadratic formula, this really isn't too difficult to do because it's pretty straightforward. You just have a formula that you can solve for, and then you use the x values that you find to find the roots, and then you can simplify this to try and factor out this x minus 1, if you can. We're assuming that you can, and considering this is an example video, you probably can, because if it didn't, then, well, that would be a little, a little awkward for me. But let's go ahead and apply this quadratic formula. So we have negative b plus or minus the square root of 25 minus 4 times 3 times 2 over 2a, which is 6. And then we have 5 plus or minus the square root. Well, this gives us 24. So 25 minus 24, which is 1 over 6. And that obviously is just going to simplify to 5 plus or minus 1 over 6. And that means that we have 1 and we have 2/3 for our roots. And then now we can go ahead and apply this to simplify this quadratic. Alright, and I've just gone ahead and cleaned out a little space for us to continue. So we can simplify this now that we know the roots to 3x minus 1 x minus 2/3. Beautiful. And then what we're able to do is we can go ahead and add in this x minus 1 from our initial limit, and we can cancel these out. So that leaves us with 3x minus 2, which I've just gone ahead and factored the 3 to save time, and then we can go ahead and add in this 1. That gives us, well, 3 times 1, 3 minus 2, or 1. So this limit evaluates to 1. Wonderful! Alright, here we are. So we have trigonometric substitution / identities. Isn't that a mouthful? And it just so happens to also be my least favorite method and the objectively worst method. However, sometimes there are certain situations in which, well, we have no choice. So better get into it, right? So we have, oh Christ. Alright, so let's break these down one by one to avoid breaking our computer, or whatever device you just so happen to be using. But regardless, we have definition of tangent here, which is just sine over cosine. If you've taken any trigonometry, you probably know this. So what we can do is we can take this limit and we can substitute the definition of tangent in, and this will give us some like terms because we just have tangent and sine. So let's try to put things in terms of sine. So doing that, we get sine of x over cosine of x over sine of x. Alright, well, that makes things a little more manageable. So now what we can do is we can go ahead and multiply the numerator and the denominator by sine of x. And that means that these sine terms cancel out, and that gets us sine of x squared over cosine of x. Excellent. And now when we go ahead and plug 0 in, so recalling some of our basic values from trigonometry, we can remember that sine of x is just going to be 0, so this squared term doesn't actually do anything. And then cosine of 0 is going to be 1. So that gives us 0 over 1, no more pesky indeterminate form, which means that this all evaluates to 0. Alright, there we go. We have our first trigonometric limit. Wasn't that fun? And it only gets better. Okay, here we have our next one. It's an exciting one too. So we have 1 minus cosine of x over secant of x minus 1. And what we're able to do is, although this problem is very clearly a little bit more difficult, we can use the same methodology. So we have an equation with secant, and based on its definition, we can convert this into terms of cosine, which is what we're dealing with. So let's go ahead and do that. So we substitute 1 over cosine into this. So that gives us 1 minus cosine, 1 over cosine minus 1. And then to further simplify this, we can go ahead and convert this 1 into terms of cosine. So that gives us 1 over cosine, and the reason we're doing that is so that these share a denominator, and then we can write this as 1 over cosine over 1 minus cosine, all of which is over cosine. Beautiful. Take a shot every time I say cosine, huh? And then we have this, so we can just multiply both sides by cosine. So we can multiply by cosine over cosine. And what does this give us? Well, these cosines will go ahead and cancel out. These 1 minus cosines will cancel out, which just leaves us with, well, what do you know? Cosine. Cosine of x to be specific, and now that we have this, we can substitute 0 in, and this provides us with 1. All of this evaluates to 1. Alright, folks, we're on to the last one. So we have cosine squared of x over sine squared of x minus 1. As x approaches pi over 2. So we don't appear to have any terms of tangent or secant, nor do I see anything immediately obvious. However, we do just so happen to have the Pythagorean identity listed here, which could be of assistance. So we can try to think about converting the sine squared x minus 1 into terms of cosine, see if we can simplify. So how would we do that? Well, we can go ahead and think about this as just a regular equation that we're trying to solve for cosine squared. So we can go ahead and subtract sine squared from both sides, and that will cancel out this sine term, so we have cosine squared is equal to 1 minus sine. Alright, well, we don't quite have that down here, but what we can do is go ahead and alter this so that we switch these signs. So we have 1 minus sine squared over cosine squared. And what this does is now we can actually just substitute in cosine squared. So that gives us cosine squared over negative cosine squared. And, well, obviously these are going to just cancel out, and we're left with 1 over negative 1 or negative 1, which means this evaluates to negative 1. We don't even have to use substitution. We just have a clear answer here. Voila! And there we are. That's our very last question. Alright, that's all for today. Thank you sincerely for watching. Before we close out for today, I will just go ahead and add that there are many, many more trigonometric definitions that I could not possibly all list here. So just be aware of that. There may be some important ones that you want to memorize. But yeah, there we go. That's all the problems for today. So I will see you next time. If you enjoyed, maybe enjoyed is the wrong word to use here. If you learned something, then I'd appreciate it if you'd leave a like or subscribe. And I'll see you next time, hopefully. Have a wonderful day.